The next example we'll look at is example 3. Let's suppose that 2 dice are rolled, and we want to find the probability that the second dice is a 4, given that the first die is a 4. So let's let event A be that we get a 4 on the first die, and let event B be that we get a 4 on the second die. The probability of getting a 4, given that the first die showed a 4, is still going to be 1 out of 6 because the presence of the first event isn't going to in any way, shape, or form change the structure of the die or the number of 4s that exist on the die. So the probability of B given A would be 1/6. Similarly, the probability of just rolling a 4 in general would be 1 out of 6. So because the probability of B given A is equal to the probability of B, we would say that events A and B are independent. And intuitively, this should make sense because whatever happened on one roll of a die isn't going to impact or influence what's going to happen on the second roll. Let's take a look at another example. Let's suppose that we draw 2 cards from a deck of cards, and let's suppose that the selection is done without replacement. Let's let event A be that of drawing a 9 on the first pick, and let's let event B be that of drawing a 9 on the second pick. If we want to calculate the probability of B given A, so what is the probability that we pick a second 9 given that we had a 9 on our first selection? Well, if the selection is done without replacement, then when we choose the first card, if we're given that we got a 9, then we look at that 9, we pick it out of the deck, and then we would remove it from the deck. Which means that when we go to make our second selection, we are now working out of 51 cards. Furthermore, the number of 9s that would be left at that point in time would be 3, because we've previously removed 1 from the deck. So that would be 3 out of 51. And if we just ask the question, what's the probability of just getting a 9 in general, the probability of getting a 9 on one selection would be 4 out of 52. We see that these two probabilities are not equal to each other. Therefore, events A and B would be dependent. And typically, in my opinion, as you kind of go through mathematics, every time you kind of get an example of a definition, it's always good to have an example that kind of matches with that definition so you can kind of see how it works in practice. In general, if you want to look at a classic example of dependent events, a classic example of dependent events would be drawing 2 cards without replacement. That will always produce dependent events because no matter what you got on the first card, because it's being removed from the deck, that second selection is now taking place out of 1 fewer cards, and that will always produce dependent events. Let's take a look at example 5. They ask us to determine whether the event would be independent or dependent. If we look at the event of not putting money in a meter and the event of getting a ticket, those 2 events would be dependent. In other words, not putting the event in a meter would definitely influence it. That would actually increase our probability of getting a ticket. So because event A will impact the probability of event B occurring, those 2 events would be dependent. In the next example, let's suppose that we have balls numbered 1 through 52, and they're going to be randomly picked by some kind of lottery machine, let's say. If we pick 2 balls, and if the selections are going to be done with replacement, then these 2 events would be independent, because no matter what we get on the first pick, the probability of the second event occurring would be the same as the probability of that event occurring regardless of whether the first event had happened or not, because we have the full assortment of balls to select from when we do our second pick. So anytime the selection is done with replacement, the 2 events will always be independent. This now brings us to the multiplication rule. The multiplication rule gives us a way of calculating the probability that 2 events will occur in sequence. So let's suppose we want to calculate the probability that event A occurs and then also afterwards event B occurs. This is going to be equal to, first of all, we need for event A to happen first. And we know that A happens with probability P of A. If we're successful and if the A and B event happens, then first of all, A has to occur, but then in addition to that, we need B to occur after A has already taken place. And that takes place with probability B given A. So the probability of A and B is equal to the probability of A times the probability of B given A. This formula will simplify a little bit. If A and B are independent events, then we recall that P of B given A is simply equal to P of B, and then we would see that P of A and B is simply equal to P of A times P of B only when events A and B happen to be independent. Let's take a look at example 6. Suppose we're going to select 2 cards from the deck without replacement from a standard deck. Let's find the probability of selecting a king and then selecting a queen. Again, because the selection is being done without replacement, these 2 events will be dependent events. Let's denote A as the probability of getting a king on the first pick, and let's let B be that of getting a queen on the second pick. According to our multiplication rule, the probability of A and B occurring is the probability of A times the probability of B given A. Well, what is the probability of getting a king on the first pick? Well, we have 52 cards at that point, and there's 4 kings in the deck, so that happens with probability 4 out of 52. If we're successful, and let's suppose that we do indeed get a king on our first pick, we remove it because it's without replacement, the probability that we would then get a queen on the second selection would be the following. There's still 4 queens left in the deck. We're now pulling out of 51 cards, so it's going to be 4 divided by 52 times 4 divided by 51, and if we simplify that, that will simplify to 0.006. So 4 out of 52 times 4 out of 51 would give us our final answer of 0.006. Let's do another one. Again, suppose we're selecting 2 cards without replacement from a deck. Find the probability that both cards would be heart cards. So there's 13 heart cards. We have the numbers 2 through 10, which is 9 digits. We have the face cards, Jack, Queen, King, and then there's also the Ace of Hearts. So that's 13 cards altogether. Because the selection is done without replacement, these will certainly lead to dependent events. The probability of getting a heart on the first card and then also a heart on the second card would be, first of all, the probability of getting a heart on one pick. There's 13 hearts in the deck out of 52 cards. So that would happen with probability 13 out of 52. If we are successful on the first pick and we do get a heart, we pull it out of the deck. When we go in to reach in for our second card, the probability of getting a second heart, given that the first card was a heart, there's now 12 hearts remaining out of 51 cards. So that's going to be 12 out of 51. And according to the multiplication rule, the final answer should be 13 out of 52 times 12 out of 51, which would be 0.059. So this is the probability of selecting 2 hearts in sequence without replacement. Let's look at example 8. Suppose that we toss a coin and we also roll a die. Find the probability of tossing a tail and then rolling a 3. These 2 events, so the event of tossing a tail and the event of rolling a 3, these events should be independent because no matter what happens with the coin, that's no way, shape, or form going to influence what's going to happen on the die. So these 2 events will end up being independent. Therefore, our multiplication rule will simplify. The probability of A and B is simply going to be the probability of A times the probability of B. The probability of first flipping a tail, that's 1 out of 2, so that's going to be 1/2. The probability of rolling a 3, that's one side on a die, that's 1 out of 6. Therefore, the probability is going to be 1/2 times 1/6, which would give us 0.083.